Thank you for the introduction. So the talk, my talk this afternoon is entitled Restocking the Optical Designer's Toolbox for Next Generation Wearable Displays. I've been involved in developing design tools as well as fabrication tools for microrefractives, diffractive optics and holographic optics for the past 2 decades. And since about 4 or 5 years, I'm also with Google, especially Google X, which is a subpart of Google. Or should I call it no alphabet? I don't know. So these are a few projects that we're working on at Google X. You can recognize, of course, the self-driving car project Glass, in which I was involved deeply. The smart contact lens project, Project Loon, Project Wing, the drones, and some other projects like Project Mechani, which is a kite wind turbine. Now, some of these technologies rely heavily on optics, especially Google Glass, the smart contact lens, and of course the sensors on the self-driving car. Now, this is the fullest extent with which I'm going to talk about Google Views, and about technologies developed at Google. The rest of the presentation is more my own personal view of where the industry, wearable display industry is today, where it will go, what are the underlying optical technologies today that fuel this market, and how these optical technologies will actually evolve to restock the optical designer's toolbox to develop next generation wearable displays. So the outline of my talk is as follows, 4 points. We'll review today's smart eyewear, AR, augmented reality, and VR, virtual reality headset markets. Then we'll try to see what actually fuels the current market hype. Then we'll see how was today's optical designer toolbox stocked up to address these current requirements. Because we didn't invent the wheel, we actually used technologies that were developed previously, and how we use these technologies and how they are evolving. And of course, what's next in the optical designer's toolbox. Today's smart eyewear, AR and VR headset markets, well, near-to-eye displays is of course a natural evolution of information technology that puts not only the computing power not only the computing power on your head, actually part of the computing power is in the cloud, but also puts on your head the interface and also the display. And in most of the cases, a see-through display, which doesn't alter your natural field of view. That would be smart glasses and AR. Head-mounted displays are not new. They're actually pretty old. And the defense industry has usually started to use such devices back in the 60s. There also has been some early adopters in Hollywood, which also, of course, contributed to create the hype. Smart glasses and related technologies have come a long way from defense to consumers. So first defense, and here we have an example of a father and son. So the son actually went for the defense green CRT. Yes, there's a CRT in there. Monocular HMD. And Dad went for Google Glass, which is a consumer RGB LCOS-based smart glass, which is Google Glass. And these two are actually used today. There's a big price difference between the defense monocular and consumer monocular. So, this said, I think I want to start by explaining, I mean, most of you might actually know, how to build the optical backbone of a head-mounted display. What does it take? What are the basic building blocks of a head-mounted display? Could be a smart glass, could be an augmented reality headset or virtual reality headset. Well, we'll start with some imaging optics. These imaging optics can be standard refractive, reflective, gradient index elements, total internal reflection, freeform lenses, diffractive lenses, Fresnel refractive lenses, or even holographic elements, volume holographic or thin surface relief holographic elements. Then you have to add a very important component, which are the combiner optics. So first you image, and then you combine. In case of a smart glass or an AR device, you actually combine the field with the digital information. And usually these optics are very different from the imaging optics. So you can actually think about a halftone reflective mirror. You can think about dichroic reflectors, leaky diffractives, leaky holographics that either work in free space or guided space or even waveguide space. Then you might actually add something else, which industry calls an exit pupil expander, that actually expands the exit pupil of the optical system. And in most of the cases actually replicates this exit pupil so that the smart glasses or the augmented reality headset can be worn by people who have very different IPDs, interpupillary distances, without having to readjust the optics to one's head. So you want to have a large exit pupil, and therefore you might want to use exit pupil expander technologies, which are, for example, diffuser, microlens arrays. So people use diffusers, microlens arrays in pupil forming architectures, leaky diffractives, leaky holograms, volume holograms, cascaded dichroics in waveguide in a waveguide confinement, and also cascaded prisms. Then, of course, you need a good display source. And actually, this is the first thing that you should think about when designing an optical system, is the display source. That can be an LCOS, which is what was used in Google Glass version 1, a liquid crystal on silicon reflective display. You can actually use also a transmissive LCD. You can actually use a micro OLED display, an optical with a silicon backplane, micro LED display. You can use a laser MEMS scanner, a fiber scanner. All these are used today. Or even a phase panel, a dynamic diffractive. Then you might add some other optics, such as gaze tracking optics, which track your gaze and can actually track your gaze as overlaid over the virtual display. This can be done in either direct imaging mode or scanning mode, waveguide scanning mode. So both are implemented today. They can be implemented as an independent optical path superimposed on the display optical path, or they can share optical elements. So the display path, the digital display path, can actually share optical elements with the gaze tracking path. But one is a finite conjugate system, and the other one is usually an infinite conjugate system. And of course, you can spice it up, as Emerald would say, by introducing some optical gesture sensing and head tracking sensors. This is really to spice it up. So by using direct imaging, structured illumination, time of flight, using infrared MEMS scanner, shadow imaging using flood, IR illumination, etc. So the timing doesn't work. I'm just telling you, it's still on 40 minutes. So the current tools available to the optical engineer are as follows. And this is what industry is using today. Thank you. So this is the way I really like to depict optical technologies. It's on a two-dimensional graph on which you have a delta n. What is delta n? It's basically the index differences of your optical elements. Is it air into plastic? Is it plastic into plastic? Is it plastic into glass? Is it high index glass into low index glass? Is it some kind of index modulation? And on the horizontal direction, you have the size of the structures that are composing this optical element. And that structure, I would call that structure large lambda, which is actually a period in a grating, for example, divided by the reconstruction wavelength, which in our case will take green. So for ratios of 100, of course, and larger, 1,000, 10,000, you have refractives, green elements, and reflectives. Then you go down around 110, you have Fresnel optics, but these are micro-refractive optics. And then you go down to diffractives, which are operating in the scalar or in the vector regime. You also have waveguides, planar waveguides or patterned waveguides. And then you have volume holograms. Volume holograms have the lowest delta. We'd like to push it up a little bit, but it's very difficult. Diffractives can have a higher delta index because they can be etched, so it's air to plastic or low index plastic to high index plastic. In volume holograms, usually people are limited to a delta N of about 0.1 or 0.05, depending on the materials. So these are the current technologies that are available to the optical engineers. These are some of the current consumer offerings. And in the wearable display space, and you see that there are a lot. I'm classifying them into 3 different categories. First category, smart eyewear. A smart eyewear, there's the word eyewear. So it's a natural extension of glasses. So a glass becomes intelligent. In the morning, you want to put on your smart glasses. First of all, because you want to see yourself in a mirror. If you need prescription lenses, that's the first functionality. And then, of course, oh, by the way, it can give you digital information. It can augment your life. But this is really an extension of eyewear. When you go to AR headsets, such as Microsoft HoloLens, this is more like an extension of a computer on your head. In case of VR systems, such as the Oculus, this is more like an extension of a gaming device. That's today. That doesn't mean that this is going to be true tomorrow. These 3 products might merge if the optical technologies evolve in a way that allows them to merge. But today, this is, I think, where we are. The requirements. So here you have a graph that shows the target specifications for designing and fabricating a smart glass AR headset or VR headset, and then 4 different categories. First category would be the smart eyewear. Second category would be VR headsets. Third category, the AR headsets, and of course, defense HMDs, which we're not so interested in today. So the target specs are very different. So if you see a plus, of course, means very important. If you see minus, that's not so important. So for smart eyewear, the industrial design is very important. It's actually the most important thing. Then comes power requirements. Then comes costs, weight, and the eye box. You want to share your glasses with your friends who have a different IPD, so you have to have a large eye box. In defense HMDs, you wear a $300,000 HMD, and usually it's actually made for you. So you don't really need to share it with a lot of people. In VR headsets and AR headsets, more bulky headsets, you can actually have a mechanical adjustment of your IPD. Prescription integration, very important for smart eyewear. Not so important for defense HMDs. If you need prescription eyewear, it's very unlikely that you will fly a multi-million-dollar jet fighter anyway. In AR headsets and VR headsets, prescription integration can actually be implemented as an add-on feature, which makes it very bulky, but it's possible because these are headsets, these are not smart eyewear. Full color operation, very important, of course, for VR headsets, and AR, not so much for smart eyewear. Field of view, of course, that's the main difference. Smart eyewear, 15 degrees or so, 20 degrees is okay. AR headsets, you really want to go over 35 degrees. VR headsets, you really want to go over 90 degrees. And of course, defense HMDs, you really want to go over 100 degrees field of view. Okay, so smart eyewear is more a consumer fashion statement in the digital world than anything else. This is very different from AR headsets and VR headsets. And I showed two examples, Microsoft HoloLens and the Oculus. Field of view and field of view location, today we have a zoo. There's no standards. On this graph, you have a few field of view representations. If you have a black edge, that means it's an occlusion display. If you have a white edge, that means it's a transmission, a see-through display. So you have a few contenders here. You can see some of them have very small field of view, contextual display, glanceable display. Some have very large field of views for an augmented reality immersion or even a virtual reality immersion. It's very interesting to plot these devices over a 2D graph. In the horizontal axis, you have the field of view, which goes up to 100 degrees or even larger, up to 200 degrees in some cases. And on the vertical direction, the functionality. Is it a smart glass? Is it an AR device? Is it a VR device? So you can see that there are actually very specific groups appearing. First, you have the connected glasses, which have no display or maybe just a single display, single pixel display. Then you have the small field of view occlusion monocolors, such as the Vuzix M100. Then you have medium field of view see-through monocolors, like Google Glass. We talk about smart eyewear here. And then you go to the eyewear arena, where you have a whole aggregate of products which are using very different optic technologies, diffractive, holographic, cascaded mirrors, cascaded microprisms, you name it. And then you go to VR, in which, for the moment, the optics are very simple, but that is going to change. And there you see companies such as Sony, Zeiss, Samsung, Oculus Reality, and Star VR, which claims to have a very large field of view. Of course, field of view is one thing, so you can image a large field of view, but you have to populate that field of view with pixels. And usually, you want to go down to the limit of the human visual system, which is about 1.2 arc minute. So if you want to fill out a 15-degree field of view, such as in Google Glass, well, you can use an NHD 640 by 360 pixel display. If you want to go to AR applications, such as 50 degrees, yeah, you need to go to 1080p displays, which actually pump more power. They are more bulky, and then if you want to go to larger field of views, for example, well, not that large, but maybe just 90 degrees, you need a 4K UHD display. And this is going to be the next Galaxy Note 5, which doesn't exist yet. Well, I think will be available pretty soon. The 2K QHD is the Galaxy S6, which will actually allow you to go to around 50 degrees field of view in a 16:9 aspect ratio. So you see, having a field of view, designing an optical system that provides a field of view is one thing. Populating it with pixels is another thing. And these are some of the micro display technologies that are used today in industry in HMDs and smart glasses, going from LCOS to LCD to OLEDs to laser MEMS scanners and even fiber scanners. So are smart glasses, AR and VR technologies going to take over our lives? Well, what fuels the current market hype? Well, the Gartner cycle, the Gartner hype cycle is actually published every year. This is the latest version. And I spotted seven technologies linked to smart glasses, volumetric and holographic displays, wearable user interfaces, augmented reality, cloud computing, virtual reality, gesture control, and speech recognition. These are all today on the official Gartner hype cycle. And you see most of them actually passed the hype cycle. Today, as a fact, we are, since about 2013, but more like 2014, in a VR AR investment type. This is from National Venture Capital Association, and this is actually the money that venture firms have put in emerging virtual and augmented reality projects. You can see how it goes up. MIT Technology Review, which is a very serious review, reviewed Magic Leap as one of the breakthrough technologies of 2015. Magic Leap, developer of augmented reality headsets. Now, if you don't know what to do this evening, you can just go to any newsstand. This is the current edition of Time magazine. You can buy it today. It just came out today, a few days ago. This is Palmer Luckey. This is the founder of Oculus. And that, of course, a cover of Time generates a lot of hype. This is a market analysis of Yole, a French market forecast analysis for wearables, putting it at $100 billion market value in 2020. And here, augmented virtual reality forecast by DigiCapital shows actually that the main lead will be AR and not VR in terms of revenues, as you can see in 2020. So here are a few major moves in the VR AR arena. Facebook buying Oculus in 2014 for $2 billion, Google investing $500 million in Magic Leap, Apple buying Meta. There's an acquisition frenzy at Intel, buying Reckonjet for $175 million this year, investing in Vuzix, $28 million this year, acquiring two Swiss startups, optical startups, Composite Labs and Lemoptics, and of course forming an alliance with Luxottica, eyewear company. They also develop new wearable chips, such as Curie, Edison, and Quark. There's more startups that raise more dollars in the AR/VR field than any time in the past. Meta raises $23 million. Meta is developing AR headsets. Augmedics, developing applications, raises $60 million, and so on. There are other moves in the gesture sensing and depth mapping fields. Microsoft acquiring Cadesta, gesture sensing. Apple acquiring PrimeSense, PrimeSense being the company that developed the Kinect sensor for Microsoft. Intel acquiring Tizix, and Google working on Project Tango. There are also another slew of companies that are involved in this gesture sensing. So how was the current optical designer toolbox stocked up to address current requirements? Or rather, how was the current optical designer's toolbox stocked up to fuel the growth of the smart glass AR/VR markets? We don't have to go very far away in the past. SPIE and during the International Year of Light went up to Ibn al-Haytham. We just need to go back a few decades, 2 or 3 decades, to understand what happened. The successive market booms, hypes or bubbles which have fueled the growth of underlying optical technologies. I have 5 of them here. But in order to understand what happened, you actually want to look at the NASDAQ composite index and the huge drop in 2000. Subprime mortgage financial crisis was scary, but right now we're here. We actually surpassed the historical maximum of the NASDAQ composite index. We're right there. Let's go back to 2000. This is a Forbes magazine that touted the coming light years with over-optimism in optical technologies by fear of missing out investors and market analysts. One example is the computer of the future that Fortune magazine actually introduced. Just reading it quickly, for decades, silicon, with its talent for carrying electrons, has been the mainstay of computing. But for a variety of reasons, we're rapidly approaching the day when electrons will no longer cut it. And well, what else? Optics. Well, so what happened the last 10 years? These are the 10 worst performing stocks of the past decades. And of course, the old category winner are the financial institutions. The second worst one, optics, is a fact. 10 worst performing stocks of the last decades. course, Kodak filed for bankruptcy because didn't diversify. One diversified, one did not. JDSU was the other winner, which is now called Viavi or Lumentum. It actually looks like a direct function, but with two peaks, very important, because the first peak is actually dot-com crash, and the second peak is the optical telecom crash. Some of you are actually old enough to remember this crash. JDSU buying SDL in the largest high-tech deal ever for $41 billion in stock. And then again, New York Times quote, until 2001, the worst annual performance for an American corporation was $23 billion losses by General Motors. But of course, it was smashed by JDSU with $56 billion. Same thing with Nortel, same type of hype curve. Nortel bought a company called Kairos Photonic Switching, but bought it based more or less on a PowerPoint file for $3 billion. And of course, as New York Times again quotes it, telecom giant Nortel filed for Chapter 11 bankruptcy protection in Delaware today for bad management and bad acquisitions. So what's the lesson? Well, no matter how high, and I want you to go out and take this with you, not the tremendous hype and losses of optical companies. No matter how high and how low optical companies' stock rise and fall, the underlying optical technology is developed with hype market investment money never goes lost. Investors of course lose money, but the optical technologies stay with us. Let's review a few of such examples and how they help fuel the current AR/VR market boom. Optical computing bubble. Well, that's a thing of the past, and SPIE knows this very well. We don't talk a lot about optical computing anymore. One technology that was born in the optical computing heydays is the optical clock broadcasting in the H3 diffractive waveguide, which is now used as the same. So this is a SEM photograph of structures in the H3 optical clock broadcasting, and this is a SEM photography of the combiner waveguide diffractives in the Nokia smart glass prototype. Might also be used by Microsoft HoloLens and Vuzix AR2000. BAE system uses a little different one, but that is an example of how one bubble fueled optical technologies for another hype. Optical telecom bubble. Static and switchable holographic technologies, especially for DWDM, CWDM, switchable optics, dynamic gain equalizers, MEMS mirrors, such as Lucent Sidewave, OMM, right here in San Diego, deformable membrane devices by Bell Labs, fueled or lead the way to today's smart glass technologies such as SPG Labs switchable combiner and SPG Labs scanning eye gaze tracker, or Lem Optics Intel VCSEL MEMS projector, or also a very large field of view dynamic projection combining optics for HMDs as with Unistra. Pico projector, Pico bubble. I call it a Pico bubble because it was a very small bubble, didn't last very long, but a lot of technologies were developed, such as Intel LCOS microdisplay, laser scanner displays, which are now leading the way to gesture sensing markets, such as the ones that are used in combination with AR devices, such as in the Meta Pro, in the DK1, in the DK2, and in Lumus bubbles. Data storage booms, very interesting. Of course, you had the three booms, CD, DVD, and Blu-ray, followed by another little boom, actually triggered by quotes like running into the superparamagnetic limit of hard disks within 200 gigabytes per square inch leads us only one solution. This is a holographic page data storage. Of course, that fueled the holographic page data storage bubble, which in turn fueled the generation of holographic materials by companies like Bayer, DuPont, DNP, and Digilens. And these holographic materials are now used in smart glasses, such as in the Sony, Konica Minolta, Digilens, and composite Lem Optics. Ophthalmic prescription lenses boom. This is not really a boom. This actually, I haven't listed it as a boom. This is a natural evolution of ophthalmic lens design and fabrication. These are new freeform ophthalmic lenses as alternatives to lower performance progressive lenses in design, fabrication, metrology, leading the way to today's total internal reflection freeform optical combiners, such as the one used in Canon HMD, Motorola HC1, Kopin Verizon GoldenEye, and Imagine AR displays. So what's next in the Optical Designer Toolbox? Well, first of all, let's see where they're actually going to be positioned on the head. In fixed-wing aircraft in the 60s, HUD fixed right in front of your head. Then you go to rotary wing aircrafts with a helmet-mounted display. That's actually where HMD comes from. It's not head-mounted display, it's helmet-mounted display. And then head, starts with H also, it's very nice, it's the same word. HMDs, head-mounted displays, then smart eyewear, closer and closer to the eye, smart contact lenses, smart intraocular lenses, retinal implants, and why not visual cortex implants. So you see how slowly we go inside the brain. So looking ahead, a few among many others, these are not the only ones, but a few issues that need to be addressed today, and there are many others, but I don't have time to discuss about them, is perfecting the imaging optics, making them smaller, better, and cheaper. Perfecting the combiner optics, and remember, these are different optical blocks. Making them thinner with a better see-through experience. Reducing AR/VR nausea in binocular devices. If no optical solution exists, well, then don't throw the paper away. Look at dynamic optics rather than static optics. And of course, perfecting miniaturization and manufacturing techniques. So one thing that we actually helped promote is work by Federico Capasso at Google Harvard. These are nano antenna optics, which actually we challenged this group to come up with a complete achromatic lens that actually has high diffraction efficiency and same diffraction angle for a wide variety of wavelengths. They actually succeeded in it. The efficiency is still low. These are technologies that will be applied, well, they might be applied to telecom first, but they might be applied to display in a decade or so. This one example, perfecting combiner optics see-through. Why not using parity time symmetric optics? So this, for example, grating, in which the index is non-Hermitian. That means that n star is equal, n star of minus r is equal to n being the complex index of refraction, complex because we're going to modulate the material not only with phase, such as a regular volume hologram or diffractive, but also with loss and gain. So this is an active material. The non-hermicity of the index requires that the gain-loss modulation is phase shifted by 90 degrees to the phase index modulation. And this provides an asymmetric diffraction pattern, which in turn provides, can provide a very good see-through. But how to fabricate it? I have no idea. I'm sure somebody's going to come up with a good way to fabricate this in mass in the next decade or in the next 2 decades. Third, reducing AR/VR nausea due to the focus convergence disparity. Well, here we already see a few solutions that have been derived. Light fields using various implementations, such as the NVIDIA microlens array-based light field, the NVIDIA Stanford Tensor light field, the Lusovu light field based on holograms, and other companies also. Making optics smarter, as I said, you're in front of Zemax, you're in front of Code 5, you're in front of any software that you want. You're designing an optical system, there's no solution. Don't throw the pen away. Think about dynamic optics. And I've shown you some examples previously on how dynamic optics were included in optical system in order to provide a solution where static optics cannot provide any solution. With true dynamic holographic displays, for example, such as the one used in HoloEye, light blue optics, and the serial. And finally, perfecting miniaturization and manufacturing process by using 3D printed optics, such as with Luxocell. and even printing green optics, such as the ones developed by SPG Labs. They had a good paper a few months ago at an OSA show. They actually showed some holograms on curved surfaces with green lens modulation. So in summary, where are we standing with our newly restocked toolbox to design next generation C4 HMDs and smart glasses? Remember, this is the slide that I showed you at the beginning. The current optical technologies that are used by most HMD, smart glass and VR developers. Well, I can restock it by including, for example, microgreen optics, subwavelength resonant subwavelength resonant gratings, volume holograms on curved surfaces, as SPG showed, DigiLens actually, surface plasmons, photonic crystals, metamaterials, PT symmetry optics, so metamaterials would be metasurfaces as the one developed by the Capasso group, and PT symmetric optics as the one that I showed you before, based on the gain-loss index modulation. Of course, that's not all. You have to have, along with these new tools in the optical designer's toolbox, techniques such as light field displays, tensor displays, technologies such as dynamically reconfigurable optics, refractive optics, diffractive optics, why not holographic optics, and new fabrication techniques such as freeform optics and printed optics, both surface and gradient index. Thank you.